Hi, I'm Eric. My partner Jack and I worked on a game called CS470 Party for our project. Every screen in our game is rendered using React Canvas elements, and players advance around our board by selecting and playing different minigames from our minigame library. This is the home screen of our game. From here we can either choose to view the high score page or play the game itself. We use Axios to talk to our API server, which queries our high scores database, sends the data it receives back to Axios, and is displayed in our high scores page. These are the 10 highest scores that have been logged to our database. Going back to our home screen, we can press play to move to our player select screen. On our player select screen, the player can select from 1 to 4 players and can choose to enter custom player names which are displayed on the screen. If no name is entered for a player, a generic player X-type name will be used. The player can press play to launch the main game, which displays all player names and scores at the left of the scoreboard. The player whose turn is currently up is displayed at the top of the scoreboard, and player tokens corresponding to player color are initialized to the start square. The player up can roll and play a random minigame from our library, and will advance their token upon successful completion. This first minigame is a 2-player rocket avoider, where the player that has lives remaining advances. One player controls their ship with the arrow keys and the other with WASD. After the game ends, the player's scores and positions are updated and the next player's turn is up. We have both 1 and 2 player games in our library. The first 1-player game is called Breakout. The player controls a paddle with the mouse and must try to keep the ball from touching the floor while at the same time scoring points by hitting the bricks with the ball. When the minimum score is reached, the score turns green and the player will advance. After the game, the points are added to the player's score and the token advances since we scored over the minimum.
This is a baseball typing game where you type words in to bat balls away that are slowly coming closer to your screen, and this is done by taking a word list, sorting it by the length, and then slowly displaying harder and harder words as the time and the inning goes on. This is Connect 4, except you're playing against an AI player. So what happens is you play as blue, you choose a piece, and you set a piece down, and then immediately once you do, an algorithm fires off called the min-max alpha beta cutoff, which is a long name, but essentially what that does is it's going to start looking at different boards, and it's going to look at the best board for a move, and then it's going to look at how you would move the best to counter that board, and it's basically going to go down and look at all these different boards, and eventually it's going to get to a point where it cuts off, which is where the cutoff comes from, to save time, and then it's going to evaluate each of those boards and see which one is the best one. So the way I have that set up is I'm using a heuristic that is the amount of connections on a certain board. So for example, let's say that there's a board that has 3 red connections, where all red has to do is put one more piece. It's going to like that board, so it's going to prioritize it and possibly choose it over another board. So then it gets sent to the main screen and makes a move, and then you keep playing until the game is over. This is 2-player Pong, done by looking at the position of the ball and updating it based on whether it hits a player's paddle or the sides of the top and bottom of the screen, and first to 3 wins. This is Pac-Man, in which you move the pack around the maze to gather as many cherries as you can, and your efforts are hampered by 3 different ghosts that spawn throughout the game. All of the ghosts use a path to get around, and I was able to find these paths by taking a pre-made Pac-Man board, setting it to my screen, and then I found the information of every single pixel in the screen, and I was able to transcribe that into an array that shows me whether a path is black or blue to find where the ghost can go. Each of the 3 ghosts uses a different pathing algorithm to find its way to the Pac-Man. The blue one ends up going random different places to find it, and the red one ends up using something called Manhattan distance, which finds the farthest distance it is from either the X or the Y coordinate, and then it'll bounce around and see if it has a move to go there, and if it doesn't, it'll go to the next farthest distance. And the gold ghost will actually use a BFS search. This BFS search will perfectly search the fastest route directly to the Pac-Man, and the ghost will start moving in that direction. If it reaches that destination and the Pac-Man still isn't there, it will update with another BFS search, and after every few seconds, it will update with a new path anyway. This is Puzzler. It's a 2-player game where people move simultaneously by moving a pill to the left, right, and also rotating it, which is reflected on a 2D array for each player. And the goal of the game is to match up the colors. Once you get 4, a break happens where those pieces will break and disappear. And after that, any piece that is connected on the board to nothing, so it's floating in midair, will turn into a droplet. This dynamic droplet object will stay in a list, and it will be taken off that list once it falls down due to gravity and hits the next object. And the way I'm able to do this is by evaluating all the pieces from the right to left, bottom to up. And because of this, I'm able to change each droplet in that order by gravity, so a droplet doesn't fall within another droplet that has yet to be updated. Both players play for 1 minute each, and the goal of the game is to rack up as many points using different positioning strategies and taking the fall from gravity into account to get the highest score in the shortest amount of time. This is Snake. It's played using a 2D array for the board as well as a queue for the snake. So every few seconds, depending on the direction of the snake, which is dictated by your arrow keys, the snake queue will update and then be reflected on the board, and then it'll check the entire board if the snake is hitting itself, a boulder, or a vulture, and the boulders and vultures randomly spawn throughout the entire duration of the game, making it harder. And the boulders will spawn wherever your snake is not at, and also the vultures will have their path tested to see if it's possible to avoid them. This is Tetris. You can move the piece left, right, and then rotate it, just like any other Tetris game. The way the rotation is done is you take a midpoint that's on a certain, it's different for each piece, but basically you take a midpoint, and then you store that, and then you perform a rotation, that's a matrix rotation, and then you transcribe it using that midpoint to put the piece in the correct position. And then from there, it's just classic Tetris. You stack up different lines and you try to get a Tetris, which is 4 lines. And if you're able to get 4 lines at a time, you get double score, and basically you just play for a minute.
Once one player reaches all the way around the board, the game ends and the winning player gets 1,000 points added to their score. Once player Hey wins the minigame and advances, the end state is triggered and we move on to the end screen, where all player names, scores, and their positions are displayed. On this page, we send the player's scores through Axios to our API server and store them in our database. We can press the back button to return to the home screen. Thank you for your time. I hope you enjoyed our project.